Now let's discuss finding the x and y intercepts and using that to actually graph our linear equation. Here's an example where we show the particular points that we outlined earlier as what we call the x and y intercepts. Again, the x-intercept is just where our graphic crosses the x-axis, the y being where it crosses the y-axis. Now there's something particular about these 2 points that we point out in the graphic here that show that the x-intercept always occurs when y is equal to 0, and the y-intercept occurs when x is equal to 0. No matter what our particular linear equation looks like, this is always going to be the case. Now, in all of these examples, I've mentioned that we really only want to find 2 or 3 points along the line to represent the entire solution set. And so if we're careful about the values that we choose to actually select and substitute into our equation, we can make this an efficient process. And using the intercepts is one of the most efficient ways to do this because substituting in 0 is typically very easy computationally and simplifies our equation nicely to where we really only need to find these 2 points, and that's enough to create the graphic. So visually speaking, I should be able to point out, as in these 2 cases, what the x and y components of the intercepts are. For instance, in my first graphic over here, I would say that my 2 intercepts are nice and visible here and here. The components for each, the x-intercept here would be at 4, 0. The y-intercept occurs here at 0, 2. And as for the other example, I have my y-intercept here at 0, -6, and my x-intercept here at 2, 0. Again, we have to note that the x and y intercepts have those corresponding zeros values exactly where we should expect. In most cases, though, you won't have a visual to identify the intercepts. More likely, you'll be given an equation. So we have to refer always to our sort of basic definition of that intercept to remind ourselves of this heuristic that you see on the right. If I want the x-intercept, I'm going to substitute in y = 0 and solve for x. However, if I want the y-intercept, I'm going to do the opposite, letting x = 0 and solving for y. But we can perform this operation as if we were just choosing arbitrarily values for substitution. Creating my xy list again, I'll recognize that, for instance, letting y = 0 as opposed to x is no different really than solving this equation as we did before, except without being so arbitrary, we're being specific about choosing x and y = 0 so that we can find these intercepts. When I use y = 0, my equation becomes 2 times x plus 0 = 8. And so I get a solution of x = 4. And if I do the same for x = 0, I get 2 times 0 plus y is equal to 8. And I get a solution of y = +8. So in the corner here, I'll draw my graphic. I have now for my intercepts 4, 0, and 0, 8. So this is hand drawn, so it won't be super accurate. Let's say that this is 4, this is 8 in the positive direction. This is 4, this is 8 in the positive direction. So plotting my x component, the x-intercept here at 4, 0 would be somewhere around here. And 0, 8 represents my y-intercept. That's going to be somewhere like here. So with those, I can get a sort of rough sketch of what this thing looks like. Now, graphing a line using the intercepts is usually not so rudimentary. We may have some digital version to help us graph, but for the most part, even a graphing calculator does this the same way that you would. It creates an arbitrary list of x and y values that are very close to one another, makes the substitutions, and just plots with as much fidelity as its screen will allow. So as humans, we got to be a little bit smarter about how we do this. We don't want to be a computer and list a bunch of x, y values. So again, all of the topics within this section are based on how do we make quick work of plotting some graphic equation that has literally infinite many solutions. So here again, we are asked to graph using the intercepts for the following equation. In this format that we're expecting, this is actually in the standard form of the equation. So again, if I want to find my x and y intercepts, my x-intercept is where y is equal to 0, and my y-intercept is where x equals 0. Substituting here, I get x minus 2 times 0 equals 4. My solution just becomes x equals 4 again. And for my other substitution, I get 0 minus 2 times y is equal to 4. And in this case, I get y is equal to negative 2 for my solution. Again, I can separate it over here and create my plot. So let's say this is 2 and 4, and this will be negative 2, negative 4. Plotting, I get 0, or excuse me, 4 comma 0 for my x-intercept occurring here, and 0, negative 2, my y-intercept being here. So the equation here actually calls for a fairly shallow steepness for the particular line that creates our linear equation.